A very good morning to one and all. Now, myself, J. Anusha, working as lecturer in physics under the Department of Technical Education, Telangana. I am working in general department at SS Government Polytechnic, Zahirabad, and I am dealing with the subject applied physics for first year, second sem students. And the subject code for this subject is 18 common 203F. The topic what we are discussing in this class is from electricity and measuring instruments. And for today's session we are going to learn about ohmic and non-ohmic conductors, and also the dependence of resistance on temperature. For this we are using, I am taking help of PowerPoint presentation. The main objective of today's class is, on completion of this period, you would be able to understand what are ohmic and non-ohmic conductors, and also you're going to learn about temperature dependence on resistance, which is known as temperature coefficient of resistance. Now, let us recall what we learned in the previous session. In the last class, we studied about introduction to electricity, definition of electric current, and also we learned about Ohm's law and its explanation. So, what is electricity? Now, the matter is, it consists of many atoms. In atoms, again, we are having positively charged particles and negatively charged particles. Now, electrically, the force between these two particles is balanced in nucleus, but when we give some external force to this atom, there may be gain of electrons or lose, there may be loss in the electrons. Now this gaining or losing electrons leads to electrons to flow. So this flow of electrons is simply electric current or electricity. Now it is expressed in amperes, that is SI unit of electric current. Now the relation, or else I should say, the flow of electrons is because of potential difference across the conductor. Now the relation between this electric current and potential difference is expressed by Ohm's law. Now electric current is directly proportional to potential difference at constant temperature. Now by using this relation, we got an expression V equals to I into R. We have seen the three different expressions for V, I and R by using a triangle. So that we learned in the previous class. Now this is our today's session about ohmic conductors and non-ohmic conductors. What are ohmic conductors? The conductors which obey Ohm's law are called ohmic conductors. Simply a very easy definition here. The ohmic conductors are the conductors which obey Ohm's law. Now examples: metals like gold, platinum, iron, aluminium and resistors are best examples for ohmic conductors. Now let us see the relation between I and V here, you can see as they are directly proportional in Ohm's law. According to Ohm's law, I and V are directly proportional. So as ohmic conductors obey Ohm's law, we got the graphical presentation is like a straight line which is passing from origin. So this is the relation which expresses ohmic conductors. Now non-ohmic conductors. The conductors which does not obey Ohm's law are called non-ohmic conductors. Now here are some examples: semiconductors, diodes, transistors, thermistors, rectifiers, vacuum tubes are non-ohmic conductors. What is this? What is the definition? The conductors which does not obey Ohm's law. As they don't obey Ohm's law, what it means, I and V are not directly proportional. So they are expressed like, you can see here the relation between I and V is like a curve which shows us that it does not obey Ohm's law. That is, I and V are not directly proportional. Next, temperature dependence of resistance, or simply it is coefficient of resistance which is depending upon the temperature. The cause of resistance in a material is because of interaction between electrons and interaction between electrons with the lattice or with the atoms. So as these interactions are temperature dependent, the resistance is affected by the temperature of the material. So this temperature coefficient of resistance is defined as the factor by which the resistance of the material changes when there is change in its temperature. So this factor is temperature coefficient of resistance. Now let us see what is it, or else how we can express this temperature coefficient of resistance. The fractional change in resistance is directly proportional to change in temperature of the material. So this fractional change is expressed as delta R, which is R minus R naught, and the change in temperature of the material is expressed in delta T, which is T minus T naught. Now here the relation is delta R by R naught is directly proportional to delta T. Now if you take it out proportionality, we got a constant alpha. Now delta R is simply R minus R naught. On cross multiplying the factor in the second equation, we got R as R naught of alpha 1 plus alpha into del T. This is an equation for resistance on temperature dependence. The resistance of a material which is depending upon its temperature is given by R is equals to R naught of 1 plus alpha into del T. Now where R is the resistance at temperature T, R naught is the resistance at temperature T naught, alpha is the temperature coefficient of resistance for the material. So this is the factor which is giving relation between temperature and resistance, and T is the material temperature in degree Celsius. T naught is the reference temperature for which coefficient is specified. So here are the temperature coefficient of resistance is of two types: positive temperature coefficient of resistance, negative temperature coefficient of resistance. So positive temperature coefficient of resistance is simply indicated by PTCR. Negative temperature coefficient of resistance is indicated by NTCR. Now let us see what is positive and what is negative. For metals or conductors, the resistance of the material increases with the increase in temperature. As we increase the temperature, for metals or conductors, resistance is also increases. Therefore, they have a positive temperature coefficient of resistance. So the value of alpha is positive for metals or conductors. Now, best examples for positive temperature coefficient of resistance substances are silver, copper, gold, etc. Now here we can see the relation between resistivity and temperature for metals or conductors. You can see a curve which is showing that as the temperature increases, resistance also increases. Now, negative temperature coefficient of resistance. For semiconductors, the resistance of the material decreases with increase in temperature, which is exactly opposite as in the case of metals or conductors. So, as the temperature of semiconductor increases, their resistance decreases. So, they have negative temperature coefficient of resistance. Now, the value of alpha is negative for such type of materials like silicon, germanium, carbon, etc. Now, here we can see graphical presentation of or graphical representation of semiconductors where it is showing us the relation between temperature and resistivity. Now in the previous case we have seen the curve is increasing. Now you can see the curve as decreasing as the temperature increases. Now for insulators also, as the temperature increase, the resistance of these materials is also decreases. Now, what is the difference between semiconductors and insulators? In both the cases, as the temperature increase, resistance is decreasing. But in the case of insulators, alpha is very small. Best example for such type of insulators are glass, rubber, diamond, etc. So this is what we learned in today's session. Let us summarize what we learned. We have discussed about ohmic and non-ohmic conductors, and also we learned about temperature coefficient of resistance. Now identify ohmic conductors from the following. Now here are some materials: gold, silicon, platinum, none of the above. Now from this the answer for ohmic conductors are gold and platinum. The value of temperature coefficient of resistance of gold is 34 into 10 power minus 4 per degree Celsius. So this is what we learned in this session. I hope so. Here the answer, it is indicating as silicon, but it is gold and platinum. So this is about ohmic and non-ohmic conductors and temperature dependence on resistance. The resistance which is depending upon the temperature, it is expressed as coefficient of resistance which is depending on temperature. It is of two types, positive and negative. For metals and conductors, it is positive. For semiconductors, insulators, it is negative. So, with this, I am concluding this class. Thank you so much for listening it carefully.